Hey guys! This is lesson 1.5, which is on relative velocity. And so this will be our last lesson for this unit. Okay, so relative velocity is the velocities of two different objects relative to each other. If we were to compare both of those velocities, it might look something like this. So when you compare, you want to find the difference, right? So what is the difference between them? This subtraction means that there are going to be different answers if you put your B first and then your A. So just make sure that you're going in the right order. If they say object A relative to object B, they mean A minus B. So I don't know if that really explained what relative velocity is. Let's give you a scenario. Okay, so we have two vehicles. Pretend that the bus is object A and the car is object B. So when we find the velocity of the bus relative to the car, we're comparing the bus to the car. So the car is the one of importance that we want to put from the perspective of. And I don't know if that makes a lot of sense. And so here's a little tip that we use, like math teachers, that's what I mean by we. Okay, object B rhymes with me. I'm going to put myself inside the car and I'm going to compare the bus to myself. I'm always going to put myself in the perspective of object B. So whenever you see object B, like relative to B, think of relative to me. If I'm the one inside the car, I want to see how fast or slow the bus seems to be compared to myself. And it really depends on the situation. So for example, if the bus is going in the same direction, I mean, you've probably been on the road and been beside another vehicle before, it doesn't seem like it's going very fast compared to yourself. And that's because both of you are going in the same direction. If one's a little bit faster and you decide to subtract your speeds, like there's not very much of a difference. Whereas if I put the bus over here and make it come towards you, well, it's coming in your direction at its speed and you're going in its direction at your speed. It's almost as if you're adding both of those speeds together and you are then like surpassing each other or meeting each other very quickly. Okay, I mean, sometimes you almost feel the magnitude of that meeting when like a gust of wind from the other vehicle almost knocks you over, right? So it rattles your car or something. Anyway, I'm getting a little bit too deep into this, so I would like to show you an example. I'm just hoping that you have a little bit of a better understanding for relative velocity. Okay, example number 1. Consider a highway situation. You have a car, a bus, and a truck. So here's your car, your bus, and your truck, and I've given them variables, okay, for each of the vehicle's velocities. I'd like to draw some of their vectors over here, and so I've made them all pretty with different colors. That's how we're going to keep track of them. Okay, so the car travels at 140 kilometers per hour west. Let's draw a vector. Okay, so we're going to go west like that. The bus travels at 80 kilometers per hour, so it's a little bit slower, and it's also going in the same direction. So same direction, but less of a magnitude. So we're going to draw a smaller arrow. Lastly, we have the truck, which travels at 60 kilometers per hour east. And so we're going to make it go in the opposite direction, and it's even shorter than the other two. Okay, so I think I'm ready to start calculating some stuff. Find the velocity of the car relative to the bus. A relative to B, relative to me. I'm going to be inside the bus and I'd like to see what the car does beside me. Okay, like what's the velocity like? I mean, even logically, we can figure out that obviously if the car is going faster than the bus, it's going to surpass me, but by how much? Like, what's it going to seem like? Okay, so what we're going to do is we're going to take car minus bus. Okay, so car minus bus, we're going in the same direction, west, and so you just subtract. And as we said, I mean, 60 kilometers per hour, that's not very fast. The car is going to surpass me, I'm inside the bus, by 60 kilometers per hour. Okay, so it's going to seem slightly faster than us. All right, let's try the second question. Find the velocity of the truck relative to the car. Relative to me. I'm inside the car and I want to see how fast that truck seems to be coming at me. Okay, because it's going in my direction. All right, so truck minus car. Here's the velocity of the truck minus the velocity of the car. Already you've seen that, like, you see a little bit of a problem. The 60 minus the 140, you're going to get like negative 80. That doesn't even make sense. Like, what is negative 80 kilometers per hour? Okay, and if you have east and west, like, how do we combine those? Those are different directions. So what you might want to do is see if you can switch one of them to the same direction as the other, and then you can combine both of the components together. Okay, so the negative 140 kilometers per hour, I'm going to separate that. Just put a plus in front because a plus and a minus still make a minus. Okay, and then knowing that it's going west, why don't we flip it? And if we flip it, we'll take that negative and we'll change that to the opposite direction. So now we're actually going 140 kilometers per hour east, which matches the other one. So we can just add them together and that makes a lot of sense. Like the truck, I'm in the car. The truck should be coming towards me or seem like it's coming towards me very fast. Okay, let's try example number 2. This is going to be a little bit trickier, mainly because, well, we aren't talking about land vehicles anymore. We're now talking about water vehicles. And so we have different units. Instead of distance being measured in, say, kilometers or miles, a ship, when it's sailing, will be in nautical miles. And so anytime you see this capital M, think of distance. Okay, now knots, if we take a look at the units, is nautical miles per hour. So if you think about it, that's kind of like a speed, but for the sea, I don't know. Okay, now what we're going to do is we're going to keep that in mind while we're drawing the diagram. A ship is steering east at 15 knots. Okay, so remember that's a speed. Why don't we draw it out? And this is going to be just my conceptual diagram. Okay, so this will be the velocity of the ship. And then it says a tug. So a tug is like a tugboat. Like, I don't know if you've seen cartoons, you know, like it goes put, 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 and kind of just drags along something else like cargo. Maybe I watch different cartoons. I don't know. So it's a tugboat and it's going to start 2 nautical miles. So that's distance, right? South of the ship. And it seems to be steering at a north 45 degrees east at 20 knots. Again, so that's a speed. Okay, so why don't I fill in that diagram a bit. This is going to be our VT. Okay, and that's north, this is east. So this will be 45 degrees. Oh, so since that's a 90 degrees, couldn't we also say that this is 45 degrees? That's why they had mentioned, well, instead of saying north 45 degrees east, they may as well just say northeast because that means that the vector is going straight through the middle of north and east. Okay, and this will be a distance of 2 nautical miles apart. All right, let's find the velocity of the ship relative to the tug. Okay, so ship relative to tug means ship minus tug. And if we want the velocity, what we're going to need is the speed, and we also need the direction. So we need to find 2 different things. But before that, I mean, none of my vectors are really touching each other. So I might want to draw a diagram like a triangle, just like in the past videos. Okay, so start putting our vectors together. We have this guy right here, and then this is tip to tail, like that. Okay, and I'll copy and paste this one, put that right there. and right there. Okay, so if we were to find the resultant, we would start at the tail and then go all the way to the tip. Wait, hold on. But if we do that, isn't that Vs plus Vt? I don't want plus, I want subtract. So what I'm going to do is I am going to take Vs plus the negative Vt. So I'm going to try to make it so that it's the same magnitude as this guy, but it's going in the opposite direction. And so we would say this is negative Vt. Okay? That means that if I decide to put these guys together, tip to tail, and then go all the way around, I have my resultant, which is going to be Vs minus Vt. Okay, let's make sure that no one thinks that we're dealing with this guy anymore. We'll make you dotted. And ta-da, beautiful. Okay. All right, there's my triangle. Let's start putting stuff inside the triangle. Okay, I need some numbers. Well, why don't we transfer this compass rose right to here. Okay, this was north and that was east. And I am going to move this guy out of the way. Okay, so this is 45 degrees, which then transfers in through opposite angles into my triangle happiness. Okay, and then we have, oh, didn't they give us the speeds, like some magnitudes? The ship was going at 15 knots and the tug was going at 20 knots. All right, there's my triangle. I can totally do cosine law. 15, I got my 20, I got my 45. And so you can take a look to the left in green. I found my resultant through cosine law. This is 14.17 knots. Okay, so that's how, that's the speed, it's how fast the relative velocity is, but we still need the direction. So if we were to do the direction, we would want to do it from this perspective because that's where the ship is starting. Okay, and okay, so there's a couple things: north, east, south, and west. If we were to find this angle, and that's fine, we'll call it alpha, and we can definitely do that because we have this side and its angle, this angle and its side, and so we can do sine law, and I found alpha, okay, which is 86.41. If I were to describe that, it's going east towards the south, so east towards the south, 86.41 degrees. The problem with this is it's not normal convention to use east and west as the first letter in a direction. We normally want to use north and south. Okay, so we can still use the same number. All we got to do is make sure that we go from here over to here. Okay, so start from south and go towards the east. But then I'll just call it beta, and from south all the way to east is 90 degrees. Why don't I just take 90 minus beta, 90 minus alpha, and I'll get beta. Okay, so that's 3.59 degrees, and I would write it like this. South, 3.59 degrees. Whoops. Oh, geez. Okay, one more time. South, 3.59 degrees east. There we go. Okay, and so that's much preferred because we started with south instead of east. That means that the relative velocity of the ship to the tug, which means that I would be inside the tug, okay, would be 14.17 knots at a direction of south, 3.59 degrees east. So that was a lot already. How do we make this even more difficult? Very easy. I could decide to ask you, okay, will the two ships or the two vessels, whatever, collide. Okay, so you already know that this guy is going this way. You know this guy is going this way. Okay, are they going to hit each other? If yes, when is it going to happen? If no, will the ship pass behind the tug or in front of the tug? That's actually a pretty tricky question. And so I'm going to try to draw this a little bit bigger so you can see. Okay, so no, don't do that. Yes, you come here. All right. So this is going to get a little messy. Just bear with me. I want to know when, so what time, how long does it take for this tug to reach this horizontal plane? Okay, plane as in like not an airplane, I just mean like a flat surface plane. I want to know how long this takes to reach this point because I'm going to compare that time for the ship. Like how far did the ship travel in that same amount of time? Because if it takes a certain amount of time to reach here for the tug, I want to know horizontally, what does that mean? Like what distance is that horizontally? I can't compare this diagonal distance. It doesn't make any sense. And so I want to know in that amount of time, horizontally, how far did it travel? Because if it didn't travel very far, but in the same amount of time that ship traveled very far, they'll miss each other. Okay, so why don't we take a look at the math, and I really hope that you can follow me. If you can't, just shoot me a message down below. All right, what I want to do first is I want to fill in all of the numbers so that you see them again. Okay, so this guy was at 15 knots, and this guy was at 20 knots. Okay, so remember that is a speed. Okay, so you're going to have to keep that in mind. We also had the distance, the vertical distance, which was 2 nautical miles. Okay, and this was north, 45 degrees east. Okay, actually, you know what? Why don't I just complete this triangle? Okay, so I'm going to use green first. First, what I want you to do is not find, I don't want you to find the knots, like the speed. I want you to find the distance. Because if I have the speed and I have the distance, I can figure out the time. Okay, so this is in distance right now. I want to find this distance. So I can do sine, opposite, which is this guy, over my hypotenuse, which I don't know. Okay, so we're just going to call that VT. Okay, at a 45 degrees. All right, so I did sine opposite over hypotenuse, and I found that VT is going to be a distance of 2.8 nautical miles. Okay, so remember the black is a speed, the green is a distance. Now I can find the time. How much time did this take? So that is in blue to the right-hand side. So time is distance divided by speed. So I took the 2.8 nautical miles divided by the 20 knots, and I got about 0.14 hours. So it took 0.14 hours to start from here and get to here. But again, I can't really compare that to the horizontal distance of the ship because it's going diagonal. Okay, so what I really have to do is I have to figure out later on what this horizontal distance is. Okay, but for now, why don't I just figure out, okay, well, how far did like the ship go in that amount of time? That 15 is the speed. Okay, so it's in knots. So what is its distance? Okay, so if we try to find VS in terms of distance, so what number of nautical miles, what I could do is I could just go, okay, distance is speed times time. So I'm just going to take the speed, times the time. So it traveled 2.1 nautical miles. All right, let's put that into our diagram. I'm sorry to keep scrolling up and down. Get rid of that guy. This is 2.1 nautical miles. And okay, let's go back to horizontally, what is this distance? Because then I can compare it to this guy and know if they meet each other. So if this is 45 degrees, doesn't that make that an isosceles triangle? Because you got your 45, you got your 90, that should be 45 to make 180. If this is an isosceles triangle, doesn't that mean that this is 2 nautical miles as well? In the same amount of time, the ship and the tug in 0.14 hours traveled 2.1 nautical miles and the tug 2 nautical miles. Okay, so I'm just going to say V tug, I don't know, can I say H for horizontal? I'm running out of space. You kind of get it, I hope. Okay, so there we go. The ship traveled 2.1 nautical miles east in the same direction, so horizontally. The tug traveled 2 nautical miles east in the same amount of time. Therefore, they're not going to collide because one obviously traveled further than the other. And since the ship is the one that traveled farther, 2.1 nautical miles, it's probably going to like pass by first and then the tug is going to go behind it. So we see something that looks like, oh God, this is messy. The ship's going to go like this and pass by, and then the tug I have way too many things. The tug is then going to pass by afterwards, so it's going to go like this. Okay, so I'm hoping that that made a lot of sense to you. Again, if it doesn't, feel free to ask questions if you need to. So our next unit is going to be algebraic vectors, which is a lot less messy.